Hello and welcome to Unit 2, Lines and Planes in 3-Space. So we're going to take all the skills we learned in the first unit, and now we're going to see how they can be applied. So today's topic, linear combinations of vectors. And what's the goal? You can write vectors as linear combinations of each other using appropriate methods. And you can use this knowledge to explain the difference between coplanar and collinear. Okay, so those are two major concepts, and you need to be able to explain what each is and explain the difference between them. All right, rest of the note you have in front of you, so let's just go through that quickly. We've been worried about resultants and scalar multiples of vectors. So far we've just been adding two or three vectors together. Now we want to combine the two processes that we've talked about. So linear combinations of vectors, so here's your definition, involve creating a vector. So we're creating a new vector, and we'll call it W, such that it is created from vectors U and V. So simply put, we are going to create a new vector, W, and it is done by taking some multiple of U and adding it to some multiple of V. And for those that are sitting there thinking that doesn't sound hard, you're absolutely right. It's an easy concept, and you've been doing it a little bit in the previous unit just without knowing it. So, finishing off the note here, we say that the vectors U, V, and W are coplanar, and we've talked about coplanar a bit, or all three vectors are in the same plane, and that's when you can draw all three vectors on a piece of paper. So they all exist on a flat surface. And we've talked about the concept of collinear. Vectors are collinear if and only if it's possible to find a non-zero scalar where U vector can be written as some multiple of the V vector. So nothing's really changed at this point. We've talked about both of these definitions. They were on the previous test in terms of concepts, so nothing new. All right. So let's talk about how it works. So the example, 5U plus V minus 7W equals the zero vector. So what I want you to do is I want to express each vector as a linear combination of the other two. So all this is just using your algebra skills and getting comfortable with the fact that vectors follow the algebra skills that you've learned in grade 9. So I want to find, I'm going to have to find U equals, V equals, and W equals. So we'll start with U. So I have 5U. I want to isolate U, which means I want to move both the V and the W to the other side using inverse operations. So it becomes 7W minus V. Finally, I want to isolate U. So I'm just going to say 1/5 of this side rather than divide everything by 5. It gets a little messy. That's nice and clean. So there you go. There is the U vector in terms of V and W. So it's just rearranging as if it's just X, Y, and Z, and solve for X, solve for Y, solve for Z. Okay, no catches at this point for those that are expecting some kind of curveball. Quickly finishing up the other ones then. The V vector's nice because it's already isolated in terms of no coefficient. So it's simply equal to 7W minus 5U. And finally, 5U plus V minus 7W equals the zero vector. I'm going to move 7W to the other side by itself. And then same thing, divide by 7 is the same as multiplying by a seventh. And what it does is just a little bit cleaner. You only have one fraction then to worry about. So there you go. That's taking a vector, a linear combination expression of vectors, and isolating for each of the variables independently. So nothing new, no catches there. Okay, for the vectors shown in the parallelogram, determine A as a linear combination of BC. So I got to just emphasize, here's the tail, here's the head of A. So I want to find some linear combination of A using the vectors B and C. So how does that work? Well, C goes to the diagonal, B is along the bottom, so I have to use those two vectors to end up here. So in order to get up there using those two vectors, one thing I can do I can follow the c vector all the way to the diagonal. So that means that I've traveled 2c. And then in order to go backwards or return back to the location I want to be at, I'm going to have to subtract the b vector, because the b vector is pointing to the right, and I want to actually head left. So I've got to change its direction, and that's how we change the direction, just simply changing the sign. All right. Next one, I want to write A as a linear combination of C and D. So still the A, I'm still following the green here. I want to end up here. So I have to use the vector C, and I have to use the vector D. So how can I start here and end here? Well, we're going to use vector C again. So vector A equals vector C. So that gets me to this point. Now I have to get here. And hopefully some of you are saying you got to turn the D vector around and only go half that distance. If I go the full distance, the full D, that means that I would end up way up here, which is not what I want. So I want to get half the distance. Finally, the challenge of writing vector B as a linear combination of A, C, and D. So vector B this time, this is the one I want to model or represent. I need to start here, I need to end here. So using the other three vectors, is it possible? Quite possible. Depends on how creative you want to get. So what we can do, and some people are going to say it's a bit of a cheat, but I'm going to use no A plus a C plus half a D. So I'm not going to use A, I'm going to use C, and I'm going to use half a D. With linear combinations, we don't have to use, it says that not all of them can be 0. So the C vector and the D vector have coefficients that aren't 0. So you can have one, if you're dealing with three vectors you're adding together, you can have one which has it. Or, different combination, we could have used the A vector plus none of the C vector plus the D vector, or, and you can see where there's a whole bunch of ors. So as long as you can justify starting at the tail of the vector and ending at the head of the vector, then you are correct in your linear combination. All right, now for the ones that are more challenging, and this is always one of the poor ones done on the test, and I stress it's poorly done on the test every year, poorly done on the test. So when you have a series of vectors, u, v, and w, and it's arranged in such an order, write vector w as a linear combination of u and v. So what we're going to do is we're going to take our vector w, and of course I'm going to cheat here, move it down. So w, I want to write it as a combination of u and v. So the way it's drawn, you can see that if I was just to do u plus v, it's not going to work. So I'm going to have to cheat a little bit. I'm going to have to apparently shrink v, and I might have to extend u. So I got to figure out by how much. So I need to know how much am I multiplying the u vector by, and how much am I multiplying the v vector by. So I'm looking for my values of a and b. We know that the u vector was 30 degrees away from the w vector, and we know that this is a right angle, so this must be 60 degrees. So it's a right angle triangle. Please make sure, always look for the easiest way to do things. And if you have a right angle triangle, it means you can use SOHCAHTOA. So important. Okay, so using SOHCAHTOA, I want to find the a value, and I know what w is, it's given information. So to find the a value, so this is a part, the a value, I want to use adjacent and hypotenuse. So that is a over h, so cos theta equals a over h. So that means that cos of 30 equals A, and the magnitude of u is 6, and that's from up above, divided by the magnitude of the hypotenuse, which is 12. So I have 12 over 6 reduces to a half. So 12, rearranging it, 12 cos 30 equals 6a, or a equals 2 cos 30. Okay. So there's my a value. Moving on to solve the b value, I would have to use the opposite. So that means I'm going to use sine theta equals O over H. Sine 30 equals, the v vector is worth 9, so b times 9 over, again, 12. So 12 sine 30 equals 9b. Divide both sides by 9. We end up with 4/3. So b equals 4/3 sine 30. Which means, therefore, vector w is equal to 2 cos 30 multiplied by the u vector plus 4/3 sine 30 multiplied by the v vector. So these are your scalar multipliers. They're just numbers. So your scalar multiplier. So it tells you how big or short to make that u and v vector. So there's a part done. So the key here, once you rearrange the diagram, once you rearrange the vectors to form the triangle in question, you're going to just use SOHCAHTOA. B part, write u as a linear combination of v and w. You already have an expression. So you just have to take this equation, and we've practiced rearranging already. We got to rearrange this equation and solve for u. So w equals 2 cos 30 u vector plus 4/3 sine 30 v vector. So we're just going to rearrange this equation for u. So w would equal, w, I'm going to bring the v vector over, minus 4/3 sine 30 v, which would equal 2 cos 30u. Dividing both sides by 2 cos 30. And again, don't worry about simplifying it because you don't have a calculator. I just want to see, do you understand you're rearranging for the u vector? So there is the u vector in terms of v and w. All right, so just using your algebra skills to rearrange and solve. I'll leave this part here and we'll finish it up hopefully in the next video.